And here, let me observe that the degree of the summation of two polynomials is bounded above the maximum of degree of each polynomial. But we don't have to have equality always. For instance, if you consider f as x plus x squared, g of x as 1 plus x squared, the maximum of their degree is 2. But since we're in the binary field, since the characteristic is 2 of this rational function field, we obtain the degree of the summation is 1. So we don't have always equality. And in this case, we can write minus degree of f plus g, which is bigger than or equal to minus maximum degree of f and degree of g. And when we take the maximum of two positive elements, actually, when we consider the minus of maximum of two positive integers, we can see that actually this is equal to minimum of minus degree f and minus degree g. And by the definition of valuation f and valuation g, we see that valuation f plus g is bounded below the minimum of valuation f and valuation g. And if we consider 1 over x, we can check that valuation of z by the definition minus degree 1 over x. This is minus degree 1 degree x, degree of a constant 0, and degree of x is 1. We see that we have such an element in f2 of x. And for every non-zero constant, we know that its polynomial degree is 0. And this also shows that their valuation is also 0. Here, this third property will have a special name, which will be called triangle inequality. And I will explain the motivation for this special name. Because given a discrete valuation map V, if we fix a real number C between 0 and 1, we can define an absolute value of a function in f in terms of given discrete valuation map is C to the V of X. Here X is now 0. And for the 0 function, by the convention, we will define it. Its absolute value is 0. And one of your homework will be to show that this is an absolute value on F. So that means this is a map from F to Z that satisfies this tree property. Like in the absolute value in real numbers. Only by applying the definition of this absolute value with respect to B, you can easily check that this first two property and to show the triangle inequality, we will need to use the third property of a discrete valuation map. This is why this third property is also called triangle inequality. And finally, in this video, we will see that if we have two functions x and y with different valuations, then instead of having inequality here, we always have equality, and this is why this lemma will be called strict triangle inequality. For instance, in the example of the rational function fields, let me go over here. When we have two polynomials with different degrees, always, of course, the summation, it's the degree of the summation is of these two polynomials will be the maximum of degree of nth degree g. So this is why we can get equality. But in order to prove that in general, without loss of generality, let me prove it by contradiction. First, without loss of generality, since we have this inequality, we can suppose that v of x is strictly less than v of y, and we can observe that v of minus 1 by the second property of a discrete valuation map can be written as valuation of minus 1 plus valuation of 1. And valuation of non-zero constant is 0. We have the same value. And towards a contradiction, let me suppose that here we have strict inequality. that is, suppose that v of x plus 1 is strictly bigger than minimum of v of x and minimum of v of y, then by rewriting x as x plus y minus 1 and applying the third property to this element, we see that v of x is bounded below minimum of v of x plus y and v of minus y. And as we have observed here, v of minus 1 is equal to v of y. And by our assumptions, v of x, v of y, we see that the minimum of this valuation is v of x, hence valuation x plus y is bigger than v of x. And for v of y, we also have this strict inequality. Hence, we see that v of x is strictly bigger than itself. So this is a contradiction. Hence, we have equality. So another example for a discrete valuation map can be given on algebraic function fields. And thanks to algebraic function, thanks to the structure of algebraic function fields we consider in theorem 10, let me give an example, and this is also definition. In this example, we are given a place of a function field with its prime element t, and by theorem 10, we know that every non-zero function can be represented uniquely as t to the m times u. Here t is the prime element for p, m is an integer, and u is unit in the corresponding valuation ring. And depending on this presentation, we will define a discrete valuation map from f to integers, which maps non-zero z to power of the primitive element in their representation. And conventionally, we define Vp of 0 is infinity. And one of your homework questions will be to show that Vp satisfies the properties, 5 properties of a discrete valuation map. And here let me note that this the values of the image of Vp of z does not depend on the choice of, it is independent of the choice of the prime element we consider for T. The definition of VP does not depend on the choice of T, prime element T. In other words, if we consider two prime elements for P as T and T prime, then we can observe that one prime element can be written in terms of the other one with unit coefficients, like T equal to alpha times T prime. Alpha should be unit because otherwise, if it is not unit, it is in P, it's an element in the maximal ideal P. So we can write it as T times R with an element R in OP. Then, if we write T as alpha times T prime, and if we replace alpha as TR, we get T times T prime R. But this is impossible because in this case we see that T prime is unit. But prime element cannot be unit. So this alpha is unit. Then, if we consider the representation of Z as T to the M times U, and if we write this equality in this equation, we can represent T in terms of the other prime element T prime. But since alpha is unit, alpha to the M is unit, and here U was also chosen as unit, and this shows that whatever prime element we choose, this VP of Z is independent of the choice of this. Because in both presentation, powers of the primitive elements should be M. So this is all what I want to say for this lecture, and see you next week. Bye-bye.